Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. It is an honor to be a presenter in the seminar MSCEIS 2021. I am Mutiara Maghfira from Department of Mathematics Education, Universitas Pendidikan Indonesia, as the first author on this paper. This paper title is Linearly Ordered Subgroup of a Cyclically Ordered Group which is not linear. And this is what my research has been. A cyclically ordered group is a group with a cyclic order. A cyclic order R on a group G is a ternary relation on G satisfying some conditions. The pair G, plus, R is called a cyclically ordered group. Every linearly ordered group is a cyclically ordered group, but the other direction is not true. In general, a cyclically ordered group G, plus, R is called a linearly ordered group if and only if every non-zero subgroup of G is infinite, and for every positive integer n, the relation R negative G, 0, G implies R negative G, 0, n times G. Every subgroup of a cyclically ordered group is cyclically ordered. On the article on linear cyclically ordered subgroups of cyclically ordered groups, where January in 2019, an example is constructed so that a nonlinear cyclically ordered group G can have a subgroup H that is cyclically ordered as well as linear. The point of the example we mentioned above is let G equals L dari product C, where L is a linearly ordered group and C is a cyclically ordered group which is not linear. With the ternary relation R, which is defined by Cernak on his article, we come to the conclusion of this example is that there could be a subgroup H which is linearly ordered. From this example, question appears: what if G be the external direct product of two cyclically ordered groups which are both not linear, namely C1 and C2, or G equals C1 direct product C2? Is there any subgroup H of G which also linearly ordered? Furthermore, we discuss some condition and an example that lead to the answer to this question. To see the research method, firstly, we will present some preliminary results about cyclically ordered group. First, there is a definition of a ternary relation like this. So, a ternary relation is a finitary relation in which the number of places in this relation is 3, or ternary relation R on G is any subset R of G3. Next is definition of cyclically ordered group. Let G be a group, a ternary relation R on G that satisfies the following conditions: R1 or strip, R2 or cyclic, R3 or transitive, R4 on or compatible with the operation on G. A ternary relation R that satisfies the conditions above is called a cyclic order on G. Then the pair G, plus, R is called a cyclically ordered group. If the ternary relation R satisfies this additional property, that is R5 or total, then cyclic order on G is total, and we call G, plus, R is a total cyclically ordered group. For example, first, given G, plus, less than or equal is a linearly ordered group, we can induce a cyclically ordered group from a linearly ordered group G, plus, less than or equal by define a ternary relation R like this. So it can be checked that R is a cyclic order on G. Then G, plus, R is a linear cyclically ordered group. The example for this case is the group of integer number or the group of rational positive number. Next, consider the group torus. Torus is a multiplicative group. We define a ternary relation R in torus like this. Then R is cyclic order on torus, and torus is a cyclically ordered abelian group. The next is the group of Zn. We define a cyclic order in Zn by like this. Then the finite group Zn is a cyclically ordered abelian group. Next, there is a lemma from Jakubek and Pringerova from their article. It says that a cyclically ordered group G, plus, R is linear if and only if every non-zero subgroup of G is infinite, and for every positive integer n, relation R negative G, 0, G implies R negative G, 0, n times G. Next is the example that we mentioned in the introduction. Consider the group Z under the cyclic order R1 and the group Z5 under the cyclic order R2. The cyclic order R on the external direct product Z direct product Z5 can be defined by like this. Then Z direct product Z5 is cyclically ordered. Since R2 negative 1 equals 4, 0, 1, we have ternary relation R like this, but for n equals 4, relation R is not true because it is not strict. Hence, by lemma 3.3 implies that Z direct product Z5 is not linear. However, the subgroup Z direct product 0 of Z direct product Z5 is cyclically ordered as well as linear. And the method is, based on the example above, we can construct a cyclically ordered group G, which is the external direct product of two cyclically ordered groups C1 and C2, which both satisfy the condition that those are not linear but have a linear subgroups. Therefore, the external direct product of those two subgroups of C1 and C2 becomes a linear subgroup of G. For the cyclic order on this external direct product, Cernak defines the ternary relation R on G as follows. Through this method, we can give positive answers to the question given in the introduction. Result in discussion. Let G be a group which is the external direct product of C1 and C2, or we write G equals C1 direct product C2. C1 and C2 can be decomposed into C1 equals L1 direct product C1 accent and C2 direct product. C1 and C2 can be decomposed into C1 equals L1 direct product C1 accent and C2 equals L2 direct product C2 accent. Suppose that C1 equals Q positive direct product torus and Z2 equals Z direct product Z5. Then we have the group G equals Q positive direct product torus direct product Z direct product Z5, where Q positive and Z are linearly ordered groups, whereas torus and Z5 are cyclically ordered groups which are not linear. The cyclic order R in the direct product C1 direct product C2 can be defined by R evenly if R1, if and only if R11 or R12 when A equals B equals C, or R2 if and only if R21 or R22 when X equals Y equals Z. So C1 direct product C2 cyclically ordered. Then notice that first, since R12 negative I, 1, I, we have R1 like this, but for n equals 3, relation R1 is not true because R1 is not strict. Therefore, R1 is not linear. Next, since R22 negative 1 equals 4, 0, 1, we have R2 like this. But for n equals 4, relation R2 is not true because it is not linear, because it is not strict. Therefore, R2 is not linear. It means that C1, C2, and G are not linear. But when we take the subgroup H equals Q positive direct product element 1 in torus, direct product Z, direct product element 0 in Z5 of G, relation RH on H is defined by this. Since R11 and R21 are linearly ordered, then the relation RH on H is cyclically ordered as well as linear. Hence, H is a cyclically ordered subgroup which is also linear. Conclusion is, the discussion in the last example extends in general by replacing Q positive and Z with any linearly ordered groups, whereas torus and Z5 are replaced by any cyclically ordered groups which are not linear. Given a cyclically ordered group G equals C1 direct product C2, which is not linear, where both C1 and C2 are cyclically ordered groups that are not linear. We have shown that there could be a subgroup H of G which is cyclically ordered and also linear, with the conditions that both C1 and C2 are decomposed into the external direct product of the linearly ordered group and the cyclically ordered group. That is, C1 equals L1 direct product C1 accent and C2 and C2 equals L2 dari produk C2 accent. Then take the subgroup H of G. H equals L1 dari produk identity element in C1 accent dari produk L2 dari produk identity element in C2 accent. So that is the conclusion of this paper. Thank you so much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.